Welcome to Microlecture 13, where we start thinking about how we might predict acid and base equilibria without pKa values, so qualitatively. There's a few types of problems here that you might see. The first is predicting the direction of an acid-base equilibria. The problem looks a lot like what we did in the previous video, except you don't have pKa values. The second type of problem that you might see is a question of which is the stronger acid. Again, without pKa values, you'll have to base your answer on some sort of property or characteristic of the molecule. And lastly, I might ask, which is the most acidic H in the molecule? So which hydrogen would be given up most readily as a proton? Okay, so just for example, we're not actually solving the problem here. I'm just telling you this is a type of problem that you will eventually be able to solve after we discuss a few more concepts. And so, if I were to give you an acid-base equilibrium reaction like this, without looking up pKa values, and I mean you can look them up if you want, but telling me the pKa value will be insufficient for answering this type of question, because I'm not looking for pKa values so much as I am an explanation about the structures or properties of the compounds involved that allows you to somehow determine which direction the equilibrium would be. And the strategy here that we're going to use almost all the time is going to be comparing the stability of the conjugate bases, which are often negatively charged. So whereas we tend to look up pKa values of acids when we're trying to determine the direction of equilibrium given pKa values, without pKa values, or if I ask for an explanation that doesn't include pKa values, what we typically do is point to the stability of the bases involved in the reaction. And so that would be the NH2 minus and this compound here with the negative charge on oxygen. I'll just tell you that this particular reaction favors the direction that is forward because the product here, this guy, is more stable as an anion. And so that's the type of thinking we're going to be doing. Remember that if that is a more stable compound, then it's weak. More stable means weak. And so therefore this is the stronger base, and reactions go from stronger to weaker. Equilibrium reactions favor the direction from stronger to weaker. So that's going to be the strategy, and we'll be learning how to solve this problem in the coming videos. Okay, so another type of problem that you might be given is I would give a couple of structures and ask you which of these two molecules would be a stronger acid. Okay. And so in one case we've got a carbonyl compound, carbon-oxygen double bond. In the other case we've got a carbon-carbon double bond. And we're comparing the acidity of these two based on the ability to lose the proton indicated. So it's going to be important to be able to push the electrons around to arrive at the product of this acid-base reaction. The strategy is going to be very similar to what we did in the previous problem. That is, we want to look at the stability of the conjugate bases that are formed. So again, the only way to do that is to sort of do the reaction. The mechanism, best thing you can do is write it out rather than try to do it in your head. And let's compare the conjugate base of each of these situations. Okay, so there's the conjugate base of the first situation, where we have a carbonyl, carbon-oxygen double bond, and here's the conjugate base of our second situation, where we have a carbon-carbon double bond instead of a carbon-oxygen double bond. All right, so taking a look at the conjugate bases, could you compare them and their stabilities? I think you can. You might not have the confidence that you can so far, but think for a moment right now about resonance and resonance rules and see if you can't come up with a justification for why one of these conjugate bases is more stable than another. And so in this first case, we have electron delocalization onto an oxygen atom. So the resonance form here actually places a negative charge on an oxygen atom. Okay, so there's the resonance form. Whereas the resonance form over here places the negative charge on a carbon atom. And so we have a situation that's more favorable, right? We already know that this would be considered more of a major resonance contributor than having the negative charge on carbon. And it turns out that just having resonance is going to be a stabilizing force, and we'll continue to see that theme throughout organic chemistry, that resonance equals stability. So we see resonance in both situations, but the resonance that we see in, or the first compound rather, would allow us to conclude that that conjugate base is more stable. And so this is, again, a situation where you would have to explain that, you know, this is a stronger acid because it gives rise to the weaker or more stable base. The last type of problem that you might be asked is, which is the most acidic proton in the molecule? And so we can do an example where, let's say, I give you a structure like that. It's the same thing. There's another way I could draw it, as saying that. So it's a cyano group, a C triple bond N, and given all of the protons that are there in that molecule, we would want to be able to find the one that would be most readily abstracted. And so in essence, I'm asking, you know, is it this type of proton, or is it one of these? There's 3 on this carbon and there's 3 on the other carbon, but all of those are the same. So there's really 2 kinds of protons that could be acidic in this molecule. And real quick, let's go ahead and write out the possible conjugate bases, since that seems to be the best way to solve these types of problems usually. So if I did have a base reacting, in either case, that would place a negative charge on this carbon if I chose the first proton, and if I chose the one on the bottom, that would lead to this conjugate base. So then it just becomes an issue of asking, which conjugate base is more stable. The one that is more stable is the one that's most likely to form, and it therefore came from the more acidic proton being abstracted. Okay, so this is just a quick preview to help you organize your notes. The criterion that we're going to use to fully answer those 3 types of questions that we just talked about are as follows. We're going to be looking at the stability of bases, conjugate bases, really, based on these 4 criterion. So atom first. Which atom has the negative charge? And we've talked already about how having a negative charge on oxygen is more stabilized than having a negative charge on carbon. And of course, if you can form a more stable conjugate base, then you will. Resonance. This is always a stabilizing force. So it always stabilizes a negative charge through electron delocalization. Okay, these last 2, inductive effect and orbital, we have not talked about at all yet. Inductive effect is kind of a through bond electron pulling effect, and orbital has to do with which orbital the electrons of the anion are in and how that might affect stability.